Welcome back. This is going to be the last lecture I give on smoothing. So we've had about five previous videos before this one, and this is going to be the last in this series. So let me remind you of our problem. So the general problem would be I've got P predictors, and I want to be able to predict some Y. And I don't want to have to do all the work I had to do back in the earlier chapters where I found transformations and had to add interaction terms and all those things. And so what I'd really desire is a machine learning method where I could just put my data in and the method would learn the relationship without learning the noise. All right, so that's my goal. And so what we've done so far has been to tackle the one-dimensional problem. And so let me just go over to my pad here for a second. And what we've said is, let's say we have p equal to 1 x variable, and we had some sort of a scatter plot here. And the way we've tackled this problem has been to do something local. Okay, do something local. And so either we used a nearest neighbor method and averaged points nearest the point that we're trying to estimate, or we found some fixed neighborhoods, which we've called bins, and then we go fit some sort of a function in each neighborhood or each bin. And so maybe it's a piecewise constant model, maybe it's a piecewise linear model, or maybe it's a piecewise cubic model. And what we found is that by doing things locally, we could approximate any function, any continuous function in a pretty reasonable manner. Okay, so the problem we have is we've only tackled one variable. So how do what do we do if we have multiple x variables? In real life, it's rare to have a single predictor variable. So the answer is we're going to study something called an additive model and a generalized additive model today. And then we're building up towards more general models like a tree or a random forest. So that's going to come next week. So before I really get into the additive models, I just want to tip my hat to two of my heroes. So this work is due to Hasty and Tibshirani. And so Hasty and Tibshirani are two of the authors on your textbook. And I'm proudly displaying my copy of their book. This is their 1990 classic. Just to kind of show you the importance of this work, I brought up Trevor Hasty's Google Scholar page. And what we see is this book that I just showed you is his second most cited reference. When a reference gets 10 citations, that's considered a big deal. When you get 100 citations, that's a really big deal. 1,000 is a huge deal. Well, this is like at 18,000 sites and counting. So this is a kind of a monumental work, extremely important. Okay, so what's the idea of an additive model? Well, what we're going to do is assume that our function is additive, and what that means is my y is going to be a sum of some function of the x's individually. So what's really important to notice here is that there are no interaction terms. Okay, so there are no f1 at x1 comma x2. That's not allowed. Okay, so with an additive model, y has to be a sum of these. Now, you can think about how this just generalizes regression. So what is regression all about? Well, we had things like this: beta 1 x1 plus beta 2 x2. So that's an additive model. It's a very specific additive model. If you took f1 at x1 to be beta 1 x1 and f2 at x2 equal to beta 2 x2, then we clearly have what I just wrote. You have some intercept plus some function of x1, beta 1 x1 is that function, plus some function that only involves x2, which is beta 2 x2. All right, so one of the big advantages of an additive model is that it's extremely interpretable. Extremely interpretable. So what have we been doing with linear regression all these days? Well, we've been doing things like this. We've been saying, I'm going to interpret the value of that slope. And so, we haven't really done this, but we could have. I could have said this. Here is x1, and here is the effect, E-F-F-E-C-T, on y. And so let's say beta 1 had a slope of 1. I could graph it like this. And what that's really saying is if I have a 1 unit change in x, that's how it affects y. All right, and maybe beta 2 looks something like this. So this is x2, this is the effect on y, and maybe beta 2 is equal to -1, in which case for a 1 unit change in that direction we go down by 1. All right, so the point is I can understand how x1 is affecting y by looking at that slope. All right, and really when I say I'm looking at the slope, I'm looking at a picture like this. I don't really care what the intercept is. I don't care about that. The intercept is going to be, well, the intercept plus whatever my x2 effect is. But what I'm caring about is when I make a 1 unit change in x, what happens to y? And the answer is it goes up. When I make a 1 unit change in x2, what happens to y? Well, it goes down by a certain unit on the average. All right, so that's the basic model. Now, a couple terms that you need to know. This is an additive model, and it's an additive model for the reasons I just mentioned, but also because my y is just a continuous variable, and I'm going to assume my errors are normal. Just as we did back in the logistic regression chapter, we could generalize that. And so you can generalize an additive model to produce a generalized additive model, a GAM. And a GAM is where you allow for the there to be a transformation. So we called it a link function back a couple weeks ago, like the logit, or it could be the log if it's a Poisson model. All right. And in addition to that, we can allow for non-normal errors. So instead of having normal errors, maybe I have binomial errors for a logistic regression, or Poisson errors for a count variable. So just remember, one of the key benefits of a GAM is that it's going to be very interpretable. So if your goal is to understand how an X is related to Y, GAMs will be an excellent model for you. Another advantage of GAMs we're going to see is that they're computationally fairly easy. So compared to estimating a neural network or other models that require a lot of computation, like certain support vector machines, GAMs are going to be very fast to compute. So if you have big data sets with lots of predictors, this will be a decent method for you. Well, it's not a perfect method, and the reason it's not a perfect method is that its main limitation is that it doesn't do interactions. As advertised, this is doing an additive model. It's not doing a model that captures an interaction. So remember what an interaction is. An interaction is where the effect of some x on y depends on the value of another x. So we saw how we needed product terms to capture interactions back in week 1 or 2, whenever it was. All right, well, to build up a little bit of intuition around this, I think it's kind of good to study an example of a function that we can completely understand. So I call this the parabolic sheet example. And so let's say this is the true relationship between some y variable, and I've got two x's. So it's going to be 2x1, then plus, 10x2 minus x2 squared. Now, what's important to note is that this function can be grouped so that it's additive. So I can write f1 at x is just 2 times x1, and f2 at x is just this, this parabola. And if I go down to the bottom here, I've actually shown you what these functions look like. So for every 1 unit change in x, y goes up by 2. And then here's the effect of x2 on y. It's just an inverted U-shaped parabola. So it's upside down U, what we called it back in first couple weeks. All right, well, what does this look like if I did a wireframe plot? And so here's a wireframe plot, and this is what the function looks like. Now, what I want you to notice about this is how I don't really need the wireframe plot to understand this function. So we could ask a question like, how does x1 relate to y? Well, if I take a 1 unit hop in the x1 direction, what you're going to see is that my y increases by 2 units. It's not clear from the scale, but what is clear is that when as x1 increases, y increases, and it increases in a linear way. Now, it doesn't matter what the value of x2 is. If x2 is back here, I get a positive relationship. If x2 is here, well, I get a positive linear relationship. If x2 is here, I get a positive linear relationship. So it doesn't matter what my x2 is, the effect of x1 on y is always linear. We could do the same thing holding x1 constant. So let's just fix x1 here. What is the relationship of x2 with y? Well, it's an inverted U. If I go up here, well, it's an inverted U. One way to think about this, and if you don't remember calculus, don't worry, but one way to think about this is we could take a partial derivative. So 1 plus 2x1 plus 10x2 minus x2 squared. So if I take the partial derivative of this with respect to x1, what do I get? Well, I get 2. And so what this says is, as I move in the x1 direction, my y gets bigger at that rate. Okay, and notice this does not involve x2. There is no x2 in that expression, so the slope of y with respect to x1 does not involve x2. That's what I mean by an additive model. Let's go take the partial derivative of y with respect to x2. Well, what do I get? I get a bunch of zeros, and then I get a 10 minus 2x2, and what you should note is there is no x1 in that expression. So the slope with respect to x2 does not involve x1. I don't need to consider x1 when I'm talking about the relationship between x2 and y. And so that's what's reflected in this graph. Now you're probably wondering, are all functions additive? And the answer to that is no. So very famous example is the saddle function. And so let's just go back and continue using partial derivatives. So here's the saddle function. Y is equal to x1, x2. You can see what this function looks like with the wireframe, but another way to understand this is if this is x1 and this is x2 axis, the product of two positives is a positive, the product of two negatives is a positive. Likewise, if I take one positive and one negative, I get a negative. So you can see this function coming up here and coming up here, and then going down in the second and fourth quadrants. So it's called a saddle function because that's where my legs would go. And so you can clearly see that in this plot where you've got it going up in one direction and in the other direction and going down in the others. So I could sit on this and it'd be a saddle. Well, let's go back and take my derivatives. What's the partial of y with respect to x1? And the answer is, x2. So x2 means that in order for me to understand how x1 affects y, it depends on the value of x2. Likewise, the partial of y with respect to x2 is just x1. So I can't understand how one of these x's affects y without considering the other x. So I think that's kind of obvious if we look carefully at this plot. So let's fix our x1 way back here. So if x1 is back here, how does x2 affect y? And the answer is, well, it goes down. So as x2 gets bigger, y gets smaller for this x2. What happens if I have a very large x1? Well, the answer is, as x2 gets bigger, y gets bigger. So that's this wire in the wireframe, if you will. We could do exactly the same thing if we fixed x2. So back here, if x2 is here, then as x1 gets bigger, y gets smaller. If x2 is very large, then as x2 gets bigger, y gets bigger. And by the way, if you're in the middle, we would say that the effect of x1 has no relationship with y. Likewise, with x1 in the middle, there is no relationship. That would correspond to being on one of these, one of the axes here. All right, so this is not an additive function. Just kind of a little preview of where we're going is the methods we're going to study next will allow us to understand these more complicated functions involving interactions. Well, I'm not going to get into too much detail on how additive models are estimated, other than to say use R. And so I've got a couple examples that I want to walk you through just to show you how powerful these models are. And so I hope what you feel like is it's been worth it to study all these smoothers over the past 5 videos. So I've got a data set that where I have the grade point average of an undergraduate student. I know that students' verbal score and math score on a standardized test, like the GRE, or not the GRE, this would be the SAT or the other one. I can't remember the other one, ACT or the GRE, whatever it is. And we could ask a question like, how does their test scores at the time of admissions predict whether they perform well in college as indicated by their grade point average? So this is a problem that I stole from another textbook, and I think the authors cooked the data. There are a lot of things about this that I don't really believe, but it makes for a good example, and we'll keep using it. So let's just take a look at what we have. I can fit this with the GAM function, and I think this is, so Trevor Hasty developed this function back in the early 90s, and it's really well designed because you can stick nonlinearity around any term by just adding this S function. So in the last lecture, we showed how you could do this for a single X. Here's the first situation where you've got 2 X's. So the way to interpret this is how your verbal score relates to think of this as the effect on your GPA. Okay, so there's an intercept term and then there's a math effect, and I don't really care about that. That just gets counted into the intercept for this. I'm assuming an additive model. What this is saying is, as your verbal score gets better, you tend to do better as an undergrad until some point, and then it goes down. And I don't know why that is. I think the authors cooked the data and really didn't think about it. The other thing that's very suspicious about this data set is math and verbal are uncorrelated. And so usually there's a certain correlation between your math score and your verbal score, and they're virtually uncorrelated in this data set. Another thing that you can see is there are dotted lines around this, and those dotted lines are standard error bars. So you can see the way I produce these plots is up here. I plot a fitted object. If you say standard errors equals true, you get these dotted lines just indicating how reliable your function estimate is. And then the scale argument is kind of important. So what scale says is, I want you to produce the marginal plots so that the range of the y-axis is 2.5. So notice we range from about -2 to positive 0.5 here. That's 2.5. For the math one, it goes from about -1.5 to about +1. So that's 2.5 also. It's very important to set that scale. Otherwise, you could have a very small effect that gets stretched out to fill the entire y-axis when in fact it doesn't have that much effect. All right, what is the effect of math on your GPA? Well, it looks like it's basically monotonically increasing and it flattens out a bit. Maybe it goes down, but given the size of the error bars, I'm not sure that's really the case. It's conceivable this is just flattening out. All right, let's look at the summary object now. We went over this in the previous video. The way to think about this is we're bringing in verbal as a linear effect, then we're bringing in verbal as a nonlinear effect. So in this output, remember what I said is always look at your degrees of freedom. So this is saying if I bring in verbal having a single degree of freedom, so if I brought in verbal as a linear effect, I could reject the null hypothesis that slope is 0. Likewise, I can reject the null hypothesis that a single degree of freedom allocated to your math score is equal to 0. So what I conclude is that, well, there's at least some sort of relationship there. Let's go look at the non-parametric effects. So now with the non-parametric effects, I add additional degrees of freedom so that I can capture the nonlinearity. And the fact that this p-value is so small is a signal to me that I need those 3 degrees of freedom. So if I were to delete those 3 degrees of freedom and go back to a linear model, the change in sums of squares would be, significant, indicating, I need them. Likewise, I need the 3 degrees of freedom for math. Well, that's basically how we use these GAMs. So I would look at this and see, do I need the nonlinear effect? And if I don't need the nonlinear effect, so if a p-value here happened to be very large, then I would say I'm going to get rid of the s, the smoother part, and just have that as a linear term in my model. So large p-values mean you don't need the smoother. Tiny p-values mean you do need the smoother. So just as a quick review, we went over a problem, this linear example last time, where if I cook the data to be linear, what we found was the p-value for the non-parametric effect was not significant as you'd expect, since I cooked the data to be linear. All right, so that's how we use that. Let's go look at another example. So returning to the civic participation example, I'm going to fit this as a linear spline, controlling for a bunch of other factors like the age, the income, and the education of our respondent. Technically, this is an additive model. So I have basically an elbow model for my news effect, and you end up with something similar to what we had back in, I don't know, that must have been about video 2 or 3, where the effect looks something like this. So clearly, this is the news index, and then this would be the effect on civic participation. So we'll just call that CP. And so here's the equation. If you work it out, for this news index less than 0, the slope is 0.1. For news index greater than 0, the slope is about 0.02. And what I just pointed out down here is that when I was using a smoother in a couple of videos ago, and I was only considering news index, we overstated the effect of news index because I wasn't controlling for the demographics. So we had an omitted variable bias, but we didn't really realize that back then. So if you compare this with what we had 2 videos ago, these slopes are substantially smaller, and it's our our old friend, the omitted variable bias again. So when I actually published this work with Tom Kizak is the person who was the PhD student in this case, we included a variety of controls, and you'd have to use one of these additive models to estimate it. So this is a real powerful tool. A couple more examples for us. This is an example where I was studying a grocery shopping app. And so we had a lot of questions about it, but one of the first things we did was to try to understand who downloads the app. And so I fitted an additive model. Here's an instance, by the way, where we have, did you download the app or not? And I'm going to try to predict this based on your age, income, and the presence of children. So if this is an additive model. It works just like the logistic regression one. So if I say binomial, family binomial, that means give me a dichotomous response. So let's go, stare at our these partial plots. So this is the partial effect of income on the logit of you downloading an app. And what it says is the higher your income, the more likely you are to download the app. Notice I've set the scale parameter up here, so the scale is 2, so that all of these plots have comparable y-axes. What's the effect of having kids? Well, there are 3 values of kids in this. There's 1, meaning we know you have kids, 0, meaning we know you don't have kids, and then null means we don't know if you have kids or not. And so what we see here is that when you have kids, you're more likely to download the app than when you don't have kids or when we don't know if you have kids. Now, the third plot was the age effect. And the age effect is, at first I had a hard time believing it. So the age effect says, as you get older, you're more likely to download the app until you're about 40-ish. And then the likelihood that you download the app goes down until you're about 80. And then when you're 80 years old, the likelihood of you downloading the app increases again. And so we thought, well, how could that possibly be? We then learned that this is not the age of the person downloading the app. It's the age of the delivery address. So this is a grocery delivery service. And this was the age of the head of household at the delivery address. And once we realized that, we thought, well, this maybe could be due to having an elderly parent at home. So grandma, can't drive anymore. So you have, her son or daughter or grandson placing grocery delivery requests in. And so the older you are, maybe the less likely you are to be able to get out of the house, and the more likely someone is doing the shopping for you. So it's not necessarily you downloading the app if you're 99 years old, but one of your kids is placing grocery orders for you. Now that's an effect that I never would have thought to investigate with just some sort of transformation. So the additive model allowed us to discover this relationship, and it was very interesting effect. Well, now let me talk about a few more examples on this. So turns out we can also do stepwise regression. So I want to show a special use of the step function here. There's also a step.gam function that you can use as well. But I'm going to start out with just the intercept. Then when I use the step function of the step.gam function, I can specify a scope argument. So let me make it a little bit bigger so that we can see it. And basically what this says is I'm going to trick this into doing an interaction. So I can have an interaction with a categorical variable. So is there an interaction between the age of a person with a B-spline around it and kids? So does age have a different effect depending on whether or not you have kids? Does income have a different effect? And then I'm also going to give the linear effects of both age and income interacting with kids. And so let's just go trace through what happens. So what happens is the most important term is having a B-spline around age. So we're going to start by bringing in 3 degrees of freedom, basically to capture this sinusoidal effect. So that comes in. Then what do we need next? Well, the next most important factor is we need income. So, but notice we do better by bringing income in as a linear effect than as a spline effect. So when I look at my AIC, the penalty that I'd pay with 1 degree of freedom would be 2 times the change in degrees of freedom, so 2, versus a change in degrees of freedom times 2 would be 6 with the income effect. This is telling me what I saw back here, namely, I don't need a nonlinear effect for income, so just bring it in as a linear effect. And so that comes in. So now I have age and income. Then you're going to see it wants to bring kids in. So now I have all 3 terms in, but it's told me I don't need a nonlinear effect for kids. Then if we're doing forward selection, it's going to go search through this scope of models that I gave, and it says it looks like bringing in income with kids is going to help you. So it brings that interaction term in. So now I have a nonlinear effect for age, and basically an interaction between a numeric variable and a categorical variable. And then the forward selection stops. It tries to bring in other things, tries to delete terms that I already have. All of those things would cause my AIC to increase, so the algorithm stops. So another thing we could do then is to try to interpret this model. So we could use the plot.gam command to examine the effect of age, and chances are that age effect is going to look just like what we saw before. So I'm not going to bother showing that here. What would be a good exercise, and I'm going to put this in the your turn, is to interpret the interaction for income and kids. So that'll be part of the your turns for this week. I'm just going to close this video with I'm going to show you another. This is an article that I wrote that used GAMs, and it got a lot of publicity, I think in part because of these GAM plots. We got picked up by some news organizations. The article's entitled "Too Good to Be True," and so just take you back here. Too good to be true: the role of online reviews features in predicting probability of whether you're going to buy. And so I'll put this article out on Canvas if any of you want to read it. So the point I want to make with this is we were predicting whether or not someone would buy a product. So picture yourself on a site like Amazon, and maybe you look at the reviews, the customer reviews, and some of those, the valence is going to be the average star rating for the product. So the valence of the product you're looking at is anywhere from 1 to 5. And then this is going to be the effect on whether you buy the product. And so what we found was something that was kind of surprising, but makes sense once you think about it. And that is, as the average star rating, so first off, here are our confidence bands, and they're very wide down here. So if you have a product with low valence, there's not much of a likelihood you're going to buy. But then after about 3 stars, the valence is highly associated with you wanting to buy the product. So the higher the rating, the more likely you are to buy, up until a certain point, up until you get to about 4.5 stars. And then after 4.5 stars, the probability that you buy actually keeps decreasing. So you're more likely to buy a 4.5-star product than a 5-star product. And what we suspect the reason for this is the consumer gets suspicious. So I don't believe that everybody thinks this is a 5-star review. Therefore, the reviews are probably manipulated. And I get suspicious, and so I don't buy the product. And so what got a lot of press on this was the this notion that you don't want 5-star, you don't want all 5-star reviews. You want to have at least some in there that are not 5 stars. Otherwise, you send a signal to consumers that these reviews have been manipulated. So you can see that across a lot of different product categories. You see that sort of peak at 4.5, and we wouldn't have been able to find this without using an additive model. Additive models were extremely useful to us. Okay, so that's it for this lecture and this week. We're going to come back next week and do trees, where we're going to see how to find interaction terms.